So welcome to the first technical session. So we have a simple plan for the first 2 days to cover cryptography, and today's plan is to do symmetric key cryptography. We'll see what it is, and we'll do encryption and later authentication. And tomorrow we'll do public key cryptography. Same thing, encryption, authentication. And that's pretty much it, but we'll also have in the afternoon some hands-on lab sessions just so that you can get a feel for what some of these algorithms do. Right? You don't need to do any programming, just use some programs. Okay, so also this is the first lecture. I'll spend a little bit of time doing the introduction. So we're talking about security. Of course, trust involves security and privacy, but cryptography, or at least today what we'll be talking about for cryptography is kind of for security. So we won't talk about any of the privacy aspects much. Okay, and but of course security is important because it's so much there in all our lives now, like all these devices. So earlier, Mr. Sarvade was talking about IoT, the Internet of Things, and how all our, not just our computers, but also things like planes and industrial machines, they're all connected to each other, and they're all digital. Okay, and not just that they are connected to each other, they're connected with us, right? There are all these people using these devices, and we are all connected to each other through what are our social media. And to secure this thing, whatever that means, we'll have some precise definitions of security, some aspects of security. But to make this good, you have to handle all of these aspects: the network, the devices, and when we talk about devices, there are all these layers within a device, right? There's the hardware, the architecture, the operating system, the software tools, including things like cryptographic libraries and high-level applications, and all of these connect all the way to the people who are using it. So you need to secure all of this together. You cannot do it in any one place alone. And cryptography is actually about some of the middle layers here. At least what we'll see today is mostly on are tools that are used in network security. They're high-level protocols, and on the other hand, they're general enough that they can be used when you're designing your secure architecture or when you're trying to secure your hardware. There are various tools there that can be used. We won't talk about a lot of other tools in security, at least not today and tomorrow. We'll talk about a few things in a couple of days in advanced cryptography topic. We'll talk about today is just, as I said, encryption, authentication, and two flavors of it. You could think of it as mainly intended at network security, right? To secure our communications from from snooping, from spoofing. Just want to protect communication. Okay. So again, in the previous lecture, as motivation, you saw there are many threats that are out there with different motivations, theft, sabotage, extortion, things like the ransomware at Ames that was mentioned, or spying, surveillance, and just plain accidents, right? There are all sorts of things that can go wrong, or that there are all sorts of adversaries that are attacking us, attacking everyone, and they use different attack vectors. So attack vectors, so there's a term from epidemiology. So it's like a mosquito biting you. The attack vector is a mosquito carrying the virus, and attack surface is your skin, right? So that's kind of the analogy. And there are different flavors of these attack vectors and attack surfaces. And at some level, what cryptography is trying to do is to reduce this attack surface. Reduce or maybe even eliminate some of these attack surfaces. As a very simple example, suppose we didn't have tools like encryption. You want to communicate with someone, what do? You send a message through this internet, and anybody who has the right tools to eavesdrop on communication, they can see what you're saying. Okay? So the attack surface is just the fact that you're sending this message through this internet, and the attack vector would be somebody who has the tools to, attack vector or the tools to eavesdrop on it, for instance. And what cryptography can do is just eliminate this attack surface. They can still do their listening to you, but the messages could be encrypted, and then they wouldn't get anything out of it at some level, right? So that's kind of the overall idea. Of course, that's not all to security, right? There are other things. Once if you're attacked, there was a question. You want to recover from the threat. You want to detect that an attack has happened, that your defense has failed. All of that's also, of course, part of the higher, bigger picture. But cryptography is mainly about not having those attack surfaces in the first place. And a lot of a big reason you'll see a lot of the discussion today is about attack detection, recovery, and so forth, is because cryptography has been such a good success that there is not, it does a very good job of what it's supposed to do, of eliminating those attack surfaces that we could have eliminated, so you don't have to worry about sending messages, sending your credit card information or whatever through the internet, because cryptography works well. So I don't know, this is probably too old for you. This is from about 10 years back. I don't know if you recognize the person here. Anyone? Edward Snowden. Okay. Okay. So yes, Snowden was a whistleblower. Was a contractor for the American, the U.S. Intelligence agencies, and what he showed was that how many of the countries are spying on people. Okay, people sometimes of other countries, sometimes of their own countries. And he said properly implemented crypto systems, so encryption, authentication, and so forth, are one of the few things that you can rely on. So you look inside what NSA or CIA is capable of doing. They are breaching all sorts of security mechanisms people have. But this one thing they haven't been able to breach, and properly implemented crypto systems. Of course, the proper implementation is also part of it. But unfortunately, he goes on to say, endpoint security, so things like your devices, are so terrifically weak that the adversary can frequently find ways around it. So that's a part of the security that we won't talk about today. It's just part we know how to do very well that we'll talk about, okay, the cryptography. Because even though in principle we know how to do it, there are a lot of mistakes you can make and a lot of problems that can come up. Okay, so again, kind of stepping back once more and asking, what does cryptography give you? Well, at some level, it's all about controlling access to information. Access both in terms of, what you can learn. So you want to keep some things confidential in the system, so it's usually called confidentiality. That's one kind of access, or access control. And the other is how you might change the information in the system, or how you might change it for someone reading it. So this is often called the integrity aspect of information security. Okay, so so cryptography tries to give you tools to enforce policies that you may have, saying that so confidentiality and integrity policies, or more generally access to information policies on who can access, who can have what kind of access to information. Okay, but what we're going to do today is not just keep it at these kind of high-level English terms. We would like to actually have proper mathematical definitions for this. Okay, so can we make these things formal? Okay, so to begin with, what is information? Well, that's a tricky question. So let me go back and give one take on what is information, or rather the lack of information. Okay? And the technical, so it's uncertainty, right? You don't know what happened or what it is or something. That's uncertainty about something. And the technical term for that, or technical term for how much uncertainty there is entropy. How many of you have, you all heard of entropy. How many of you have seen the definition of entropy? Okay, some of you have. the good news is it doesn't matter. We are not going to need it. But let me, it's a term that came from thermodynamics. Goes back all the way to Rudolf Clausius in the 19th century. Boltzmann, who founded a lot of the foundations of thermodynamics, and they had a notion of entropy in terms of the chaos in the system, in a thermodynamic system. But the kind of formal definition that's relevant to us came from Claude Shannon, and this is, about. So this was actually founding this field of information theory. And his notion of information, or the notion in information theory, is an inherently probabilistic notion. The idea is that you have uncertainty because there are different possibilities for some event, some random variable, some measurement, and how much entropy there is about kind of how different the system, how much entropy there is, right? Like, how much a probability distribution can take different values and measured in some way. Okay, so there's a formal definition. We don't need that. Okay, and so this was the kind of genesis of this whole big branch of mathematics and, could say computer science in some way. And the first application that Shannon had in mind was to study efficiency of communication. So compression and error correction. You have a noisy channel, you want to send your data through it. How much noise can you withstand? How much redundancy do you need to add? And you had very good answers, and it's still an ongoing area. Communication channels can get more complicated, the kind of noise can get more complicated, and so forth. But it's the second application. So soon after this paper, Shannon had another paper. It was published kind of later, possibly because it was classified when it was originally written. And that is the application of information theory to secret communication. So not just communication, now we are interested in secret communication. Okay? So this is exactly the question that, so the Second World War was kind of a time when a lot of this question became very important. There are all these stories about the German cipher machines, Enigma, if you've heard of that, being broken by the Allies and how that gave them an edge in winning the war. And so Shannon at that time was also studying this question of the possibility of secret communication. Okay? Can you make an encryption scheme that cannot be broken? The Enigma was broken. Right? And actually, it turned out to be a simple question, or rather a question with a simple answer. And this answer was this. Secret communication is possible between two parties, Alice and Bob, let's say, but comes with a catch. They need to have shared a long secret key, okay? A secret key, and it should be equally long as a message they are interested in sending, okay? After compressing the message, and so forth. So you need to have a key that you have agreed upon a priori, ahead of time, that's at least as long as all the communication you'll ever send. And that's not a very satisfying situation, right? Because you send out your armies to the field, and now you want to send, say, megabytes of data to them. Well, you should have ahead of time send so much key material with them. Okay? And when you run out of the key, you cannot communicate anymore. So, but let's look at the positive side of it, which is that it is possible. If you have shared enough key material ahead of time, the sender and the receiver, and then they can do secret communication. And that technique, or one such technique, is called the one-time pad. Okay? So let me just show you what many of you might have seen it. Okay, so let's. You can ignore the table here, it will show up in a second. So the message is a bit string. Messages can always be encoded as bit strings. That's the kind of message we are interested in. And it has a known length. Okay? There's a little caveat that will show up now and then, I'll mention it, that you're not trying to protect the fact that you send a message or how long the message you're sent, at least not in what we are going to talk about. So everybody knows that you have sent so much information. If the exact length is a problem, you can kind of pad it up, make it some bigger length, standardized length. Okay, but for us, the message is a bit string of some fixed length that you know ahead of time, and the key is a random string of the same length. So what do I mean by random string? So say the message is, for simplicity, 128 bits. The key will be 128 bits. Each of those bits is 0 with probability half, 1 with probability half. Okay, so they tossed a coin. They tossed a coin 128 times. Look whether they got a 0 or a 1, heads or tails, and that defines their key. Okay, so the key could look something like this. Okay, here it's just 8 bits. The message and the key are 8 bits. But it's important that it was generated uniformly at random. Every bit could have been 0 or 1 with probability half. So we already see that probability. If you don't believe in probability, if you believe that everything is deterministic in this world, predestined, then all this theory wouldn't work, right? So we are okay with believing. If you believe in quantum mechanics, for instance, you have a probabilistic world. So probability is fine. We can have this notion of a coin toss coming out half the time 0 or half the time 1. Okay, so keeping the philosophical questions of probability aside, the mathematical model is well defined. Every bit has a probability of 0 or 1. So something like these 8 bits, there are 2 to the 8 possible strings, and each string has exactly the same probability of occurring as your key. And it's the same key that the sender and the receiver are going to use. Right? So it's symmetric key. That's where the word symmetric key comes from. We'll keep seeing it throughout today. And we are talking about symmetric key encryption here. So that means encryption and decryption algorithms will use the same key. And the encryption algorithm for the one-time pad is the following, right? So take any message, okay? Go here. Yeah, take any message. There is nothing like the message is random or anything, right? It's an arbitrary message, a bit string. And the sender, Alice, has this message. She takes her key and she bitwise XORs the message with the key. What does that mean? At each position of the message, if the key is 0, she keeps the bit as 0 itself. If the key is 1, she will flip the message bit. Okay? So if the key bit is 0 or 1, it tells you whether to flip the message bit or not, and the resulting bit here, or bit string here, is a ciphertext. Okay? And that's what she would be sending to Bob. How would Bob recover the message? Okay, you can just do the same operation. So you got some input, now it happens to be the ciphertext, and you just XOR it with the key again. So if you had flipped a bit earlier, you flip it back. If you had not flipped it, you don't flip it. Right? That's what this is doing. So you XOR the ciphertext with the key again, then let me see. Oh well, I don't have. So it should be easy to see. Oops, sorry. Let me. Yeah. So the decryption algorithm happens to be the same as the encryption algorithm, right? You have a key, you have an input, XOR the key bitwise with the input, produce the output. So is that clear to everyone? Like if you XOR it twice with the same key, you'll get back what you started with. Okay. Okay. So this is one-time pad, and it's called a one-time pad for a good reason. You cannot use this pad twice, okay, or you cannot even use parts of this pad twice. Just to be clear, or just to be explicit, if you had two ciphertexts, C1 and C2, that were obtained from two messages M1 and M2 using the same key K, what goes wrong? Well, what essentially goes wrong is that somebody could just XOR these two ciphertexts together. And then the keys will cancel off, but the messages will XOR with each other, and you will end up with the XOR of the two messages, M1 XOR M2. And that's not good, right? That's leaking something about the message. It's telling where those messages are, which positions those messages are identical and which positions they are not identical, and that's leaking a lot of information potentially. Okay. In particular, it will tell you if M1 equals M2. That's also leaking information, right? If two ciphertexts had the same message inside them. Okay. All right. So up to this caveat, it was a good idea. You cannot. There's a main problem with this one-time pad, right? You cannot use it twice. That's why you have to start with enough key material to last your entire message communication. Otherwise, you'll be burning through your key each time you use it. Okay, so just to kind of, I said there's a scheme, but let's see, what an encryption scheme is supposed to be, the syntax of it, and the security definition. So that's what I'm going to do in the next couple of slides. What is an encryption scheme? In this case, a one-time encryption scheme, but more generally, it's a symmetric key encryption scheme. And what does it mean to be secure? Okay, we'll start that today, now, and we'll continue the definition part next time in the next lecture in the afternoon. But syntactically, this is what a symmetric key encryption scheme is. There are three algorithms, these three green guys shown here. The first algorithm is something that has to be done ahead of time. That's a key generation algorithm. In the case of one-time pad, it just meant flipping those coins, right? Flipping as many coins as you want, and that generates a key. Somehow that key has to be made available to the encryption and the decryption algorithm. It's not our problem to figure out how at this point. So that's not symmetric key encryption. That's not part of symmetric key encryption. How you got these two people to come together, generate the key, and get a copy of the key. Once you have that, both of them have that copy of the key, the encryption algorithm is some algorithm. It can be, in this case it was bitwise XOR. Oops, it could be anything. It could be probabilistic. In fact, so clearly the key generation algorithm was probabilistic, right? And you have to flip those coins. It's a randomized algorithm. Encryption algorithm for one-time pad was not probabilistic. It was a deterministic algorithm. But that's not going to work in general. We'll see why in a bit. Once you have proper definition, it'll be easy to see. So encryption algorithm is also often randomized. Essentially almost always randomized except for when you're dealing with one-time encryption. And decryption is another algorithm that also uses a key, and it, without loss of generality, is deterministic. Okay, so you'd usually think of it as a deterministic algorithm. All right, so that's the syntax. Any questions? If you have any questions, yeah. You can just ask, and I'll repeat it. Yeah.
Do they have to be different, like a different algorithm to encrypt and a different to decrypt?
So in the case of one-time pad, your question is, do encryption and decryption algorithms have to be different? In the case of is that the question? Or?
So for one-time pad, you have already explained that it's the same.
It happened to be the same, yeah.
But if you were to design a new system maybe, and let's say you have perfect randomness, so in an ideal world, would you have a separate algorithm for encryption and then a separate algorithm for decryption?
You can. So there are schemes where you'll have a separate algorithm for encryption and a separate algorithm for decryption. We will see both kinds. Okay, so it doesn't, as far as the syntax is concerned, doesn't matter. Feel free to have different algorithms. All we care about is that it should be secure. Okay. Secure in the sense of there are multiple layers of security we'll talk about, but for today we'll start with secrecy. Okay, so some aspect of integrity will also creep into security definitions of encryption, and we'll do that next time. But for now, the security requirement from an encryption algorithm is secrecy. Okay, and you kind of feel like it should have been. It was good, right? It was you bitwise XOR with this random pad. The idea is that what you'll get will be a random string. Okay, and so it should be secret. But is that message really secret? So let's say the message was just a single character for now, right? Y or N, yes or no. And no, that was our 8-bit message. Well, is a secret, that's what Alice encrypted and sent to Bob. An eavesdropper, can she guess what the message is? Well, she makes a random guess, she has a probability half of being correct, of being right, right? So what kind of secrecy is this if with probability half, which is a big probability, right? An eavesdropper can guess your message. Okay? And that's all that one-time pad is providing, whatever it's doing. Eve can correctly find the message M with probability half by random guessing. She's actually not even looking at the ciphertext. And that should give you a pause. So it's nothing wrong about the encryption algorithm. Right? There's something about the way we are thinking of secrecy. Secrecy, no matter what you do, you cannot do anything. Whatever encryption does, this adversary doesn't even care what your encryption algorithm is. It doesn't look at the ciphertext. And I said half, but it could even be worse, right? We don't know that this message is uniformly random, yes or no. Maybe 80% of the time you'll be saying yes. You encrypt that, send it. Eavesdropper says, okay, I think you said yes, and she would be right with probability 0.8. Right? That's pretty bad. Well, there's nothing we could have done about this, right? This is something Eve, the eavesdropper, could have done. Oh, sorry, forget the shares. I changed my slides, but this slide was about something called secret sharing, which we'll not talk about yet. So Eve could have done this without obtaining the ciphertext. Okay? So the point is, it was not the fault of this encryption algorithm. We should still consider this encryption algorithm good enough because it didn't leak any additional information to Eve. And that's what we care about. If she knew that this was going to be yes with probability 0.8, after seeing the ciphertext, she shouldn't know it's yes with probability only 0.6 or it is yes with probability 0.9. That would be changing her knowledge or information about this message. And what we can make sure is that she doesn't, the ciphertext doesn't give her any additional information. Whatever she already knows about the message, she knows. Okay, we cannot try to fool her into saying it's something else because she can choose to ignore the ciphertext. Okay? And this is typical of how our security definitions will be. We'll not be trying to create secrecy or create some sort of security. What we'll be trying to do is preserve or retain as much as possible given the functionality that we want, right? So in this case, if it is this message that you're trying to send, which Eve already knows something about, we cannot make it less known to her. She will know what she already knows. We don't want to change, we don't want to give her more, right? So the ideal situation would have been the message was magically transported from Alice to Bob without Eve getting a ciphertext. We want our scheme to preserve whatever security is available or secrecy is available in that setting. Okay? We'll be approximating an ideal, or we'll be, in this case, matching what an ideal situation would have given. Okay, so we'll come back to this when we get to advanced cryptography lectures, because it won't just be about secrecy at that point, and this is something to bear in mind, how we will go about defining security. Okay, so now that we settled on, there's no obvious problem, let's make sure that it actually works. I kept saying it works. So just to kind of step through that. So, Eve got this ciphertext, right? M XOR K. And the important thing is this K is uniformly random, and she doesn't know anything else about K other than this M XOR K. If she already knows something about M, that'll tell her something about K. Hopefully that shouldn't hurt us. All right, so the claim is that Eve learns nothing new about M. So let's just make sure we see that. So let's say M is just a bit, right? So 0 or 1. So let's say a 1-bit encryption. And irrespective of whether M is 0 or 1, the ciphertext that Eve sees looks the same. The ciphertext is distributed the same way. it will be 0 with probability half and 1 with probability half. To make it even more explicit, suppose the message is 0. There are two possibilities for the key. The key could be 0, in which case the ciphertext will also be 0. The key could be 1, in which case the ciphertext will also be 1. So that that is that's the effect of XORing with 0, right? It doesn't change the bit. So these are the two possibilities for the pair k comma c. When m equal to 0, when m equal to 1, it's a different pair. If k is 1, then the ciphertext is 0. Because the message is 1, so 1 XOR 1 is 0. Or with probability half k is 0, and in that case the ciphertext is 1 because the message is 1, right? But if you just look at the c part of it, which is the second coordinate in this, what you see is if m equal to 0, c is 0 with probability half, 1 with probability half. If m equals 1, c is 0 with probability half, 1 with probability half. So it's the same distribution that the ciphertext has. Okay? So her view, Eve's view, is independent of the message. As a random variable, it's independent of, if you assume there is some sort of distribution over the message. By the way, we don't assume there is any distribution over the message, right? This kind of, the formulation I have here, that for any possible value of m, the ciphertext is distributed the same way. I don't need to say anything about the distribution of the message. It's for every possible value of the message, and the probability only comes from the distribution of the key. The probability half that I was talking about here is coming from the distribution of the key. The key bit is 0 or 1, right? But still, to use, oops, did I switch off? Okay. But if you were to think of the message as having some sort of a distribution, this would be a valid statement to make, that the eavesdropper's view, which is C, is independent of the message, which is M. Okay. And that is one bit. When you have multiple bits, which is what one-time pad does, you independently encrypt each bit using a different key bit, right? So that's exactly what one-time pad did. So each bit is now a uniformly random bit. Each bit of the ciphertext is uniformly random, no matter what the message was. So for every message, the ciphertext distribution is identical, and that's what secrecy means. That's what perfect secrecy means. Of course, I'll repeat my caveat: the length of the message is revealed. Okay? And if you're worried about not revealing that, you'll have to do some padding. But you cannot make all messages of all arbitrary lengths look the same. That is just, that's an information theoretic impossibility. Okay, but you can have something like you decide you want to send messages up to certain length, then they can all, even short ones, long ones, all within that set can be made to look the same, okay, by proper encoding. So any questions on one-time pad? Okay, yeah.
So, like whenever we do this analysis, we assume that the message M has the probability half of being 0.
No, that's exactly what it's a good question, so let me repeat that. The question was, are we assuming that the message M has probability 0, or half of being 0 and probability half of being 1? No, we are not making any such assumption. I'm saying whatever the message is, the ciphertext, so fix a message, fix your favorite message, 0. The ciphertext has a particular distribution. In this case, it's uniformly random. Fix another message, the ciphertext has the same distribution. I don't care about probability of the different messages. Does that make sense? So so if the probability of the if a message was such that it's 0 with probability 0.8 and 1 with probability 0.2, well, in this case, the ciphertext will still be uniformly random. It's just that with probability 0.8, it will be encrypting as 0, but giving you a uniformly random string. Probability 0.2 will be encrypting a 1, but still giving you a uniformly random string. Okay, so we don't care about this security definition. This is the security definition of perfect privacy. For every possible value of the message, no mention of the probability of the message. For every possible value of the message, the distribution of the ciphertext, that is talking about the probability. The distribution of the ciphertext is the same. Does that make sense? Any other questions on that?
So you said that ciphertext has no impact, like even without the ciphertext, Eve could probably guess the message.
Yes.
So it is the probability of the message that she's trying to guess, and not of the ciphertext.
Okay. So if I want to model something, so the question is, if when I said something like Eve knows something about the message, then I'm talking about the probability of the message. In this definition, I don't need to care about what Eve knows about the message, but this is a way to, this definition is supposed to convince you that irrespective of what she knows about the message, her knowledge wouldn't change after seeing the ciphertext C, because the ciphertext is independent of the message. Okay. Now, when I say something like her knowledge of the message doesn't change, that's a problematic definition, just because I have to talk about, there is some sort of a distribution over messages. You have some model of the world, messages come from some distribution. We don't need that. So this security definition, even though I'm talking kind of informally as Eve doesn't learn anything about the message, this technical definition doesn't involve a probability distribution over the messages. Does that make sense? Okay, yeah. Sorry, yeah, you can go ahead. About the
Key.
Okay, so that's a separate question. How do we know that Eve has not learned anything about the key K? Here, the security holds only under the assumption that this key is uniformly random and Eve has no information about it, right? If in practice, it's your headache to ensure that, right? So this security guarantee will hold provided key. So it's not just about Eve doesn't know the key, right? The key may have biases. If you use a random number, source, random bit source, whatever, which is biased, and Eve knows about that, she will learn something about the ciphertext. So those are assumptions kind of outside of the definition or notion of encryption itself. That's something to be worried about. Yeah.
Is there a possibility that while decrypting there are multiple answers there?
Okay. So the question is, not in this case. In this case, we have a deterministic encryption algorithm. But in general, when you allow a randomized encryption algorithm, how do you ensure that decryption will get the message back? Well, you have to do something. Your algorithm has to be clever enough to retrieve the same message irrespective of what the randomness that was used by the encryption algorithm is. Okay, that's on you to design it. In this case, it's simple. We'll see in other cases how it will work. Okay, any other questions? Okay, so one-time pad, in some sense, is optimal. So Shannon said, if and only if you have this long string, can you do encryption? One-time pad tells you how to do it if you have a key. But there's another part which we are not going to do today, which is that you need this much a key. Okay, there's no magical way in which you could have taken a smaller key and got same kind of secrecy. Okay, and that needs a little bit of an argument. We'll not do it, but it's kind of easy once you have set up notions like entropy and mutual information. You can use that to do that. Okay, we'll not do that, but just you should know that this is optimal. You can do other things other than one-time pad, but they cannot be shorter. They cannot beat this. Okay. Okay. So this is kind of a very unsatisfactory situation. As I was saying, we need to, we don't want to run out of key material in the middle of sending some message, right? So let's take a second look at this question, because Shannon's way of looking at it was very nice and clean and precise, just gave us an answer that we didn't like. So let's look at it differently. So Shannon said, an eavesdropper, if you use a shorter key, eavesdropper will learn about the message in the sense that the ciphertext will have information about the message. But maybe that information is not accessible still. Okay? In what sense? In some sense, we have to make precise. We want to say, okay, it's hard to kind of use it. Like the ciphertext has some information about the message. For different messages, the ciphertext is distributed differently. But it's just hard for you to use it in a meaningful way. Okay, so use it meaningful. Well, we have to see how we'll make it precise. But the underlying notion of being able to use it is computation. Okay, and so you cannot compute anything useful with this ciphertext. That will be good enough to say the ciphertext doesn't have any, useful information about the message. Okay, so that's where now we have to go beyond information theory. We need computational hardness or notions of computational complexity. Okay, so Shannon was not worried about computational complexity. Shannon assumed, or you could say Shannon's adversary is computationally unbounded. If there is any mathematical function that's there, they can compute it, or they can get the information out of it. But that's not how real life works. Or it would have been nice if we could get security against computationally unbounded adversaries, but since we cannot, we'll just settle for security against computationally bounded adversaries. Okay, so computationally bounded meaning what? This universe is, or even this Earth or whatever, has certain number of computational power. There are only so many atoms. There are only so many, or you could work at the frequency of molecular vibrations or whatever. There are only so many cycles of computation that you can have, right? Even if you run, you can say something like all the atoms in this known universe, if they run for all the lifetime of this universe at this frequency of what are the fundamental particles, there's only so much they can do, as in so many steps of computation they can take. Okay, all of them running in parallel as if they're computers. So we can say, okay, as long as that whole universe cannot break or cannot make use of this information, we'll say that information is inaccessible, or something like that. Okay, so that's where computational complexity comes in. So it's so we want to say some things are hard, some things are easier. It's a very young field compared to the rest of mathematics. You could say so Shannon's information theory was in the 40s, late 40s. Computational complexity or computability theory came up before that. Alan Turing and others in the 30s defined computability. But it was only in the 70s that we had notions like, say, NP hardness, or the complexity clause NP. That all came out kind of in the late 60s, early 70s. These are some of the people, Cook, Turing, Cook, Karp, Levin, you would have heard of probably as computer scientists who laid the foundations of, some of the computer scientists who laid the foundations of complexity theory. So unfortunately, the complexity theory is such that we don't know a lot. Okay? There are a lot of questions. P versus NP is a question. It's not, we don't know P not equal to NP, right? And that is a problem for us because if we believe P not equal to NP, but if P equal to NP, a lot of the cryptography or everything that I'm going to talk about in the rest of the lecture will not make sense. Okay? P equal to NP in an effective way, let's say, then cryptography would be impossible. We don't think that's the case. It's just mainly just a religious belief that we think there are things like P not equal to NP, right? There are computationally hard problems with certain kind of hardness because we looked for algorithms we couldn't find and we have not been able to find, so we think there aren't. Okay? Not entirely a solid guarantee, but that's where computational complexity theory as a field stands now. So a lot of things are believed, things like P not equal to NP. And the reason we think it's or one reason this might be okay, or it's not surprising, is because it's very hard to prove things that are they may be true, but it's very hard to prove it. Okay, and we don't have the mathematical tools to start analyzing these questions in a very detailed way yet. So we say, okay, our maths is not good enough to prove that P not equal to NP, but cryptography cannot wait until mathematicians prove things because we need to use our encryption schemes today. So we are going to just make some assumptions. We're going to take some things as a reasonable assumption, and that's the basis of modern theory of cryptography. A few assumptions, few very judicious, hopefully yeah, hopefully judicious assumptions about computational hardness, and we build pretty much everything on top of that. Okay.